Well, hello again, pre-calc students. I hope that everybody is doing fantastic and then you enjoyed your weekend. It's Monday for you, not for me, of course, but it's Monday, so it is officially time to get back to work, and we move on to section 3.6 of the AP Calculus material, the chain rule. Interestingly enough, in the last set of notes for the trig derivatives, at one point in time I actually said the reason why I chose to use the quotient rule rather than the chain rule, and then as soon as I started talking about it, I was like, wait a second. Did I teach you the chain rule yet? But anyway, after I made the notes, I looked and I was like, oh, nope, chain rule's the next lesson. How about that? So, what is the chain rule? The chain rule is how you deal with finding the derivative of a function when it has another function inside of it. What does that mean? That means if the argument of any kind of function is anything other than x, there will be a different kind of function on the inside, so to speak. So we treat them as composed functions. So we say if there happens to be a function g of x hiding inside your f of x, then the derivative of the whole thing is this, which basically means find the derivative of the outside, but don't touch the inside, and then you multiply by the derivative of the inside. If you weren't quite clear on what I just said, maybe it'll make more sense once we actually do some examples. So this first example, this is a great candidate for a chain rule because the last thing you want to do is have to FOIL this thing out several times. It's a nightmare. So how do we find its derivative? Well, what we do is we say that y prime, or dy dx, because they're the same thing, is, let's find the derivative of the outside. And what I mean by that is the outside can be thought of this thing raised to the fourth power. So the derivative of the outside says bring the 4 down to the front, just using our power rule, don't touch the inside, and then drop the exponent down by 1. See, we've applied the power rule to the outside. We didn't touch the inside. Now we multiply by the derivative of the inside. And now we just look here and we say, what's the derivative of x squared minus 2x? The derivative of x squared is just 2x, and the derivative of negative 2x is just minus 2. And that's it. I mean, could you FOIL it out, distribute, factor? I mean, yeah, you could. There's a lot of things you could do, but there's really no reason to. The point is, you could plug in an x value to this, and it would give you the slope of this curve. Ta-da! Let's do it again. All right. Well, since this argument of this radical is anything other than an x, it has a derivative that's something other than 1, which means we need to use our chain rule. I don't want to use the quotient rule, so instead what I'm going to do is I'm going to bring this radical up to the top as a negative exponent. This way, I can use the power rule again. There. So when we find our dy dx, we're finding the derivative of the outside, which is 4 times something to the negative 1/2. So that brings the negative 1/2 down to the front and multiplies to the 4. That gives me a negative 2. I'm not going to touch the inside, but I will finish the power rule by subtracting 1 from my exponent, and now I'll multiply by the derivative of the inside, which happens to be negative 2. Now I am going to clean this one up a little bit just because I don't want to leave a negative power in my answer. Negative 2 times negative 2 is positive 4, and the thing with the negative exponent goes to the bottom is a radical with a cubic. You could either say inside or outside. I'll say it inside because it looks prettier. There. Finished. And that is the derivative of that ugly mess. So, how about a word problem that has some trig in it? It gives us a chance to, review the things that we just did in the last notes. An object moves along the x-axis so that its position at any time greater than or equal to 0, obviously because negative time doesn't make sense, is given by this, cosine of something. And that something is not just x or t. That means the derivative of the inside matters. It says find the velocity of the object. Okay, so we have the position. We want its velocity. Remember from previous notes that velocity is the derivative of position. So v of t, meaning the derivative of this. our chain rule says derivative of the outside. So that's a cosine of something. So our outside is cosine. The derivative of a cosine function is a negative sine function. So derivative of the outside, don't touch the inside, times the derivative of the inside. The derivative of the inside is 2t. And just to make it look prettier, we'll just call this negative 2t sine of t squared plus 1. But you don't have to do that. I just like it to look nicer. There it is. Ta-da! That is the velocity of this position function. Okay, another example. Look, we're not going to be doing anything much crazier than this. We're just using the chain rule over and over and over again. Same kind of question, only this time it's sine instead of cosine. So d dx, which means the derivative with respect to x of sine of x squared plus x. The outside is sine. So the derivative of a sine function is a cosine function. So derivative of the outside, cosine. Don't touch the inside, which is x squared plus x, times the derivative of the inside. It's going to give me 2x plus 1. And that's it. No reason to do any other work than that. A 3-link chain. What? What does that mean? What that means is, whoops, there we go. You have a chain rule inside of a chain rule. Basically, we have this. F of g of h of x. So that is going to require a double chain rule. So it's going to get a little bit crazy here. It might help if I write this with brackets and parentheses just so you can see what's really going on. So the function can be written as the tangent of. And then I'll change colors. I think that'll help also. 5 minus the sine of. There. So my 3 functions, the pencil function, the blue function, the red function. So when we find our derivative using the chain rule, we work our way from the outside in, kind of like peeling an onion. Okay. So we go f prime of x. It says the derivative of the outside, which is tangent. Well, if you remember from the last lesson, the derivative of tangent is secant squared. So we say secant squared of, don't touch its inside. Its inside is 5 minus sine of 2x. Now we find the derivative of the inside, which is the derivative of the blue function. The derivative of the blue function, well, the derivative is constant is 0. And then the derivative, and then the minus sign comes along for the right. The derivative of sine is cosine. Don't touch its inside. And the final piece of the chain, so to speak, is the derivative of cosine's inside, which is just 2. Like that. I mean, you could reorder this just to clean it up a little bit, and it does, but it doesn't really change anything. It just says negative 2 cosine of 2x times secant squared of 5 minus sine of 2x. It just looks a little nicer, but you haven't really done anything. So there you go. Derivative of the pencil mark, didn't touch anything inside the pencil. Derivative of the times the derivative of the blue function, didn't touch anything inside the blue function, times the derivative of the red function. It's going to take a little bit of practice to get used to chain rules inside of chain rules. Finding slope. That means derivative, right? It says find the slope of the tangent to the curve y equals sine to the 5th power of x when x is pi over 3. Okay, so what I'm going to do for part A is I'm going to rewrite this function so that you can see that, yes, it is a chain rule. Y equals sine x to the 5th power. So the outside is a 5th power structure. The inside is a different function, sine of x. So its slope can be found by using derivative of the outside. Don't touch the inside. So the 5 and the 4 are the derivative of the outside. And now times the derivative of the inside. Derivative of sine x is cosine x. We've been asked to find the derivative at pi over 3. That means I had to plug in pi over 3. That means I need to know what sine of pi over 3 is and cosine of pi over 3. So our slope is 5 times the sine of pi over 3 to the 4th power times cosine of pi over 3. So I'm going to draw pi over 3. Remember, picture not drawn to scale. Okay, pi over 3 is a 60-degree angle because 180 divided by 3 is 60. Across from a 60, we will always find a root 3. Next to it, there'll be a 1, and the hypotenuse is a 2. So sine at this triangle, which is y over r, would be root 3 over 2. And cosine here would be adjacent over hypotenuse, or x over r, or 1/2. That gives us 5 times. Now, 4th power means the square of the square. So if we square this root 3, we get 3. And if we square it again, we get 9. And 2 to the 4th is 16. So 5 times 9 gives me 45. And 16 times 2 gives me 32. The slope is 45 over 32. It's a little ridiculous. Part B. It says show that the slope of every line that is tangent to this is positive. That means our job is to show that the first derivative is always positive. Okay, well, let's see how we can do that. We know we have to find the derivative, and the way it's written, kind of bites. So instead, what I'm going to do is I'm going to write it as 1 minus 2x to the negative 3. There. So when we go to find its derivative, it's just a power structure, just like this one was. We have a derivative of the outside, which means bring the negative 3 down. Don't touch the inside. Subtract 1 from the exponent. And then multiply by the derivative of the inside. Well, the derivative of this linear is just the number in front of x, which is negative 2. Oop, I was about to write an x. Negative 2. Like that. Okay, we're going to have to clean it up because we've been told to show that it's always positive. These two numbers do not have negative exponents. That means they belong on the top of the fraction. And when you multiply negative 3 and negative 2, you get positive 6. And this negative exponent would come back down to the bottom to become a positive exponent. And guess what? 6 happens to be a positive number. And 4th powers are always positive. So because the top and bottom of this fraction are both positive, this derivative is always positive. It doesn't have a choice. Ta-da! Pretty neat, huh? Okay. I know I'm moving a little bit fast, but I think it's because you have the ability, it's okay because you have the ability to pause, you know, and should you need any help, you're more than welcome to shoot me a remind and ask me some questions. You know I'm here to help you. Well, not physically, obviously, because I'm not there with you, but I'm here at my house, ready to help you whenever you need me. And last but not least, the AP Calculus textbook throws in the derivatives of parametric curves here. I'm going to be honest. I can't remember if we learned about parametric curves this year or not. I teach a lot of different things. In case we didn't learn about it, a parametric curve is a way of representing things that are not functions using functions. So we would split up something that's nasty into an x function and a y function, and they're both in terms of a different variable. So if you want an x comma y, you have to plug in a t value. That means we could also find the slope of a curve like that. And the really nice thing about derivatives of parametrics is if you want to find the derivative of parametric, dy dx, it's legitimately the derivative of y over the derivative of x. It's honestly x, well, crud. It's y prime over x prime. You know, y over x is slope, right? Rise over run, so it's just y prime over x prime. Makes life really, really easy. So we've been asked to find the derivative of the parametric hyperbola between these two t values. At this point, actually, excuse me, we've been asked to find the tangent line at this point at that t value. So we go, okay, dy dx is y prime over x prime. Okay, y is the tangent of t. Well, the derivative of tangent is secant squared. There's no chain rule here because the derivative of t is just 1, so it doesn't do anything. So it's just going to be secant squared t over x prime. Secant. Again, not going to be a chain rule because the derivative of its inside is 1, so the chain rule doesn't come into play here. But this is good review from the last set of notes. The derivative of secant is secant tangent. So this gives me secant t times tangent t, which is going to simplify because there's a pair of secant t's up here, and there's one down here, so they're just going to cancel each other out like that, leaving me secant t over tangent t. Now you might be wondering if that's going to clean up any better, but this is 1 over cosine, and this is sine over cosine. It might actually do something. Let's see. 1 over cosine, and instead of saying divided by tangent, we would say times its reciprocal, right? Well, tangent is sine over cosine, so its reciprocal is cosine over sine. Oh my goodness, look at that. This thing legitimately just cleans up to 1 over sine of t, which is the cosecant of t. That's its derivative, cosecant t. So all we have to do is figure out what cosecant of pi over 4 is. That is going to be the slope of our tangent line. All right, well, picture not drawn to scale, but pi over 4 is in the first quadrant, and pi over 4 is a 45, 45, 90 triangle. That means my sides are 1, 1, root 2. Sine would have been y over r. So cosecant is r over y. Square root of 2. That's its slope. And we were given the coordinate root 2 comma 1. That means all we have to do is point slope formula. And we have the tangent to our parametric curve through the point root 2 comma 1 when t is pi over 4. You see, t is called the parameter. It's not actually a coordinate. You plug in pi over 4 to get your coordinate. So we get y minus 1 equals the slope we found times x minus root 2. And there is no reason to do anything with it past that. Just leave it like that, and life is good. And that's your whole lesson on the chain rule. It is super important that you always look out for the derivative of the inside. If the derivative of the inside is anything other than 1, chain rule is in play. And that's it. Yay! So if you have any questions, please feel free to hit me up. And if not, I'll talk to you soon. Have a good one.